Welcome to Reliability. The material for this course is taken from a reliability book which is titled Reliability, Probabilistic Models and Statistical Methods. It is in its third edition. The copyright date is 2025. It is a self-published book and is available on Amazon, Barnes & Noble, etc. In this course, we're going to look at mathematical and statistical techniques that are used by reliability engineers to design and evaluate systems. When evaluating these systems, two key questions arise. The first question is, how long do manufactured items last? This is generally a question of evaluation, and it is typically answered by collecting data on the lifetimes of these manufactured items. Second question is, are there actions that we can take to improve the system reliability? One action is to simply use higher reliability components in the system. Another action is to redesign the system and, in cases of critical components, place those components in parallel to achieve higher reliability. The mathematical and statistical techniques that are used in this class are not applied to just one industry. So, for example, they can be used on mechanical items such as an automobile or a crane, which are largely mechanical systems, or they can be used on largely electrical systems such as a cell phone or a laptop computer. We begin with the definition of reliability. Reliability is what is being defined here. And in the definition, there are a number of words that I have italicized that we'll look into as we go forward. The first italicized word is the word item. We're always looking at the reliability of an item, and the word item is used very generically here. Item could be a component in a system, or the item could be the entire system itself. When you decide what the item is that you're trying to find the reliability of, you need to define the boundaries and the level of detail associated with that item. So in terms of boundaries, that's saying what is a part of the item itself and what is a part of the environment that is around the item. Second word that's italicized here is the reliability of an item is the probability. This is to say that reliabilities are probabilities. That means the Kolmogorov axioms apply, and one of the spin-offs of those Kolmogorov axioms is that all probabilities lie between 0 and 1 inclusive. And so that implies that all reliabilities lie between 0 and 1 inclusive. Back to the definition, the reliability of an item is the probability that it will function. So when you define functioning, you have to also define the failed state. This is easy for a light bulb because if the light bulb is burning, you say the light bulb is functioning. When the light bulb burns out, you say the light bulb has failed. But with a ball bearing, for example, you may need to define a threshold. If the diameter of the ball bearing falls above that threshold, you say that the ball bearing is functioning. But if you check the ball bearing diameter and find that it has fallen below that threshold due to wear, for example, then what you do is you define that ball bearing to be failed. So occasionally you have to define an arbitrary threshold that separates functioning from failed. Back to the definition, the reliability of an item is the probability it will function for a specified period of time. Now, time will be different depending on the context of the problem. If you have, for example, a light bulb, time might be the number of hours that light bulb has burned. If you have an automobile tire, then in that case it might be the number of miles driven. If you have a switch, it might be the number of cycles. So once you get the context in a particular problem for what time is, then you have to define the units. So the light bulb, for example, the time units might be hours or months or years, etc. Finally, to finish off the definition, the reliability of an item is the probability that it will function for a specified period of time under specified environmental conditions. Oftentimes, those environmental conditions are test conditions which are specified, and they are conducted in a laboratory before this particular item is released to the public. The other set of environmental conditions are encountered conditions, often known as field conditions, which the item encounters in practice. Those two sets of conditions are not necessarily the same. So that's the definition of reliability. There are a number of high-profile reliability cases. The first one in the list here is the Space Shuttle Challenger accident. And after that accident, the Rogers Commission went back and looked at the circumstances associated with the accident, and they determined that it was the O-rings on the solid rocket booster that caused the accident. They also discovered that the launch temperature was very cold on the morning that the Challenger was to lift off, and they determined that those cold temperatures were in large part responsible for the failure of the O-rings, which resulted in the explosion of the Challenger on takeoff. Second high-profile reliability case is the Space Shuttle Columbia accident. In this particular case, as the Columbia was taking off, a piece of insulation broke loose and struck the orbiter at a high velocity. That damage to the orbiter resulted in the accident or the explosion of the Columbia upon re-entry. So it got up into space just fine, but on re-entry, that damage that was caused by the piece of insulation was what doomed its fate. You also have the 3 Mile Island, Chernobyl, and Fukushima nuclear power plant accidents. And there is some detail associated with each of those and how they came to be. The levee failure in New Orleans during Hurricane Katrina. In Bhopal, India, there was a very, very bad industrial accident. Also have the Minneapolis bridge collapse. And more recently, you have the Francis Scott Key bridge collapse in 2024. All of these high-profile reliability cases result in this case, all of them in loss of life, with the exception of the 3 Mile Island nuclear power plant accident. And so reliability concerns and how to avoid such catastrophes in the future is important. There is also a TV series that I discovered just last weekend. It's put out by National Geographic. It came out in 2024. The name of the series is Disaster Autopsy, and they do a number of different areas for these high-profile reliability cases. Some in aerospace, some in transportation, sometimes building failures, nuclear power accidents are included, fires, building fires, for example, fires that occur on oil rigs. And what they do is they go back and they look at the data that they can glean after the accident and try to determine the cause. And this is how you can get what is known in reliability as reliability growth, and that is an improvement over in time going forward as fixes are made in the system to prevent future catastrophe.